So today we're talking about triple integrals. Um, so this takes us back to, well, double integrals, which we started, what, a week ago. Um, Basically, the idea was instead of just chopping up one dimension, having a one-dimensional domain, like an interval, we started chopping up in two dimensions, regions in the plane. So we've seen this trend throughout the course. Once we kind of go from 1 to 2, then from 2 to 3 usually isn't so bad. And so voila, here's the triple integral. Now you just chop up 3 dimensions, and instead of calling the differential an area differential, right, which is what we had the area differentials here, we're going to call this a volume differential. Because if you chop up 3 dimensions, like let's say you're in rectangular coordinates, your delta x, delta y, delta z, you multiply those together, you're going to get the volume of a little cube there. Okay, and then you're integrating and we'll see this here in next week. You can get all kinds of different things with triple integrals, just like with double integrals and integrals, depending on what you're integrating and what units you have attached. For example, let's say your function was a density function, an actual mass per volume density. Then if you integrate your density this way, you're taking the density at a point times an infinitesimal volume. That would give you sort of the mass of that little point, and then the triple integral would add all those masses up to give you the mass of the solid. So there's all kinds of different interpretations you can have on the triple integral. It just depends on the context you're in. So we're going to start off, this week anyway, we're going to stick to rectangular coordinates. All right. So if last week we talked about rectangular coordinates, and then on the Friday, we didn't meet on the Friday. I gave you a video to look at for polar coordinates, in case you needed to review that. This Friday, or maybe tomorrow, depending on when we get to it, we'll be looking at sort of the generalization of polar coordinates into 3 dimensions. There's a couple different coordinate systems we can use. But this section, we're going to stick with rectangular coordinates. And so since you have 3 dimensions to work with, you've got your differential can be any one of these patterns. So this is a nice little combinatorial review here. You've got 3 choices for the first differential, whether you pick x, y, or z. Once you pick the first differential, you have how many choices for the next one. So you've got 3 choices here, x, y, z. You pick one, now you have 2. And then once you pick the second one, you only have 1 choice left for that. So that would give you a total of 6 different integration orders. If you wanted to do a 4-dimensional integral, then you have 24 different orders. But anyway, so let's take a look and see if we can extrapolate what we did in 2 dimensions to what we did in 3 dimensions. So number 1, we're just given a triple integral. Here it is. Sketch or otherwise describe the solid Q over which this integral is being evaluated. So this is setting up the solid that we're integrating over. So let's start off doing what we did with double integrals, except we're going to be living in 3 space. So there's x, y, and z. Notice here the outermost integral dx has constant bounds. So as always, so we're chopping up here x between 0 and 2. So we're chopping up the x-axis between 0 and 2. And then I look at the y. So these outermost 2, think of this as sweeping out sort of a base in 2 dimensions here of the solid. Y goes from 0 up to 4 minus 2x. I guess I should put this down here. X is between 0 and 2. And now the y is between 0 and 4 minus 2x. So y equals 0 would be the x-axis there, and it goes up to 4 minus 2x. Welcome in, Derek. So we go up to here. And so this would be that plane. Or it's not the plane, the line. So this is sweeping out this triangle here in the xy plane the same kind of way we did back in double integrals. And now the third dimension comes in. Z now goes between 0 and 4 minus 2x minus y. So z equals 0. That's just the what? That's just a way to describe the z equals 0. Yeah, it's just the xy plane. And then, so we're going to be going down here. So my z direction, we're going to start down here in the xy plane. And then we're going to go up to z equals 4 minus 2x minus y, which is another plane. So there's the z-intercept. And then you can get the x and y intercepts. And by golly, they match up right here. The xy trace of this is exactly this line here. And so you can think of the z here as filling up this solid that way. So z goes through and fills it up. So if we want to think about the kind of the motions here of what's happening, when you have this order dz, dx, dy, or dz, dy, dx, we're going to fix an x between 0 and 2. So we're going to fix an x between 0 and 2. And then for a fixed x, so we'll fix that x in here somewhere. The y is going to go from 0 to that line, 4 minus 2x. And then for a fixed x and y, the z is going to go from 0 up to that plane. Okay. And so as we move the x from 0 to 2, we're going to be filling out this solid as an aggregate of these cross-sectional areas. And if that looks and sounds familiar, it should, because that's the same drawing we had when we had the double integral, when we were integrating a function of z. But here, the solid is part of the bounds of the integral. We're integrating over a solid now. So you see what's happening here, folks? Does this tacking on the z make sense? Do you see how we get a solid out of that? X's are points. Sweep out the y's, you get a two-dimensional curve, and then you sweep out the z's. Okay. Now, how do we evaluate this integral? Well, you would evaluate this integral the same way you evaluated all the other integrals. You have an iterated integral. So you would start here and work your way out. So let's actually go through this one. We won't do all the arithmetic, but we'll do enough to make sure we're good. Because when we have a triple integral like this, once again, we're assuming that x, y, and z are now independent variables. So when we start the innermost integral here, the integral from 0 to 4 minus 2x minus y, 2z minus x dz, right? So this is like the new piece we've got here today. We're just going to integrate this, assuming we're integrating with the variable z, treating x's, and if there were any, y's as constants. So what's the integral of 2z with respect to z? So what's the integral of 2z with respect to z? That's your z squared, good, minus. Now what's the integral of x with respect to z? Treating x and y as independent variables. That's xz. And this would be going from z equals 0 to z equal 4 minus 2x minus y. And so I'd toss that in. That's the upper limit. And then the lower limit is just going to zero out. And notice now we've integrated out the z, and now we just have a function of x and y. So this would be the integral from 0 to 2 of the integral from 0 to 4 minus 2x. And you've got your 4 minus 2x minus y squared minus x times 4 minus 2x minus y. Dy dx. And now you're back into double integral territory. So now we're back to last week. Okay? Integrating with respect to y, you could, if you wanted to, do a u substitution. You could let u be what's in parentheses, and then look at the du, the dy, adjust the things. Or you could always just brute force it, square everything out, collect like terms, integrate on your way. If you go through the machinations, you should end up with 8. So it works out to be 8. All right. So once again, we're tacking on a z. We understand how to do iterated integrals with x and y, so when you tack a z on there. But it's important to understand, because I saw some of these errors on the test, but let's say you've got a triple integral here. Let's say you've got dz, dy, dx, and you've got something in here. The integrand can depend on all three of the variables, or any one or two of the variables, okay? So the integrand itself can have all three variables in it. But if you're integrating with respect to z, all right, this first integral here, this could have functions. We'll call it g1. This could be functions of x and y because you're integrating out the z. All right. Once you've integrated out the z, it can't come back. Okay, so you've integrated out. Now you would have a function of x and y. dy now, that could be, that could have x in it. And then the x, the last integral, always has to be constants. Okay, so these have to be constants like a to b or something. I guess that's the standard default, right? A to b. So once you integrate a variable out, it doesn't come back. You follow? So the last integration you do has to be constants, and then you can depend upon this variable, and then you can depend upon that variable. Okay. So that's sort of the format of the triple integrals, and you can move the letters around and all that other good stuff. We'll be switching the order here momentarily. Okay, volume using a triple integral. So I guess a precursor to this, even though we didn't really talk about it much in Calc 1, if you have an interval I, AB, you integrate over I 1 dx, you get b minus a, which is the length of I. And then if you want to get area, you do a double integral over 1 dA. So for volume, you take a triple integral over 1 dV. So if your integrand is 1, you can interpret your integral as you've taken this solid, you've chopped it up into tiny little volume pieces, and now you're going to figure out the volume of the little pieces, add them back up to get the volume of the whole solid. Right? So hopefully that makes sense. Can you see the generalization here? Integrate dx, you get the difference in x's. Integrate dAs, you get the area. Integrate dVs, you get the volume. So here's a chance for us to actually set up some triple integrals. So we're looking at the volume of the tetrahedron bounded by the plane x plus 2y plus 3z in the first octant. So just like with double integrals, the first thing you want to start off is a sketch of the region. With triple integrals, you want to start off with a sketch of the solid. And, you know, the kinds of things I'll throw at you are things that you should be able to visualize, but you also have your Desmos 3D and GeoGebra you can use as well if you get stuck. But it's going to be consisting of things that we've talked about, like, you know, planes, parts of spheres, cylinders, you know, things like that. So let's take a look at x plus 2y plus 3z equals 6, and we're looking in the first octant. And so this should take you back to like week 2. Well, actually, we've been looking at these more recently than that. Here you go. You know it's a plane because all the variables are to the first power. And when you sketch a plane, you can look at intercepts and traces. What would be the x-intercept of this plane? Yeah, so if you zero out y and z, you're going to get x equals 6. Put that there. The y-intercept, you'd zero out x and z, get 3. Put that there. Z-intercept, zero out x and y, you get your 2. There you go. And then you connect the dots. There you go. So that's the plane, and then since we're in the first octant, we're also going to be bounded by the coordinate planes. Okay, so there that is. Okay. So for us, so here's our new volume. Our old volume formula used to be the double integral of the base over the base of the height. Now we're just going to take a triple integral over the solid itself of 1 dV. So this is how we're going to use triple integrals for that. But we can still think of chopping up the base and then multiplying by the height, or integrating rather through the height. So if we go back and look, they want dz, dy, dx. So that's the first one they want, is they want dv to be dz, dy, dx. So in rectangular coordinates, when you do this in rectangular coordinates, you can still think of this as sweeping out the base, and then we're going to be integrating over the height. So you can still think of it that way. Okay. So with that in mind, let's take a look at what this thing looks like in the xy plane. So I go back to my picture, and I want to figure out what this is looking like here in the xy plane. So what's the name of this line? What did we call this back in the day? That was called the xy what? Do you remember? Yeah, the xy trace, and we can get the xy trace by setting z as 0. Okay, so that's going to be this line here. We know the intercepts are 6 and 3. Those aren't going to change, but now I've got an equation for this line. There it is. And this is going to be my base. So that's the base I need there. So when I set up my triple integral for my volume, it's going to be 1 dz dy dx. So I can work from the outside in here. So starting with the x, once again, we're going to be chopping up constants. So here's x. X is going to run from where to where? 0 to 6. For a fixed x, what's the y run between? It's going to start down here on the x-axis, which is y equals what? And then we're going to go up to here. And yeah, that's right. We got to solve this for a fixed x. How far does the y go? We've got to solve this for y. So we could subtract the x over and divide by 2. There we go. Or you could simplify it as Zoran did there in the chat. Okay. Now here's the new part. For a fixed x and y, what's the z go between? Okay. So if the height is going to be in the z direction, then what goes down here would be the bottom surface, and what goes here would be the top surface. Okay? Yeah, so if I go back to my picture here, the bottom surface, well, since we're in the first octant, it's cut off at the bottom with the xy plane, aka z equals 0. So that's the bottom. Right. Whoops. And so then once again, what we're doing is you got to imagine we're filling this up. So if I fix that x and y, it's going to go between the bottom surface up to the top surface. And once again, we need the top surface z as a function of x and y. So we know the top surface is the plane. So I need, for a fixed x and y, how far up do we go? I need to solve this equation for z. And so you could solve it that way, or you could simplify it. It really doesn't matter. Minus x minus 2. Oh, yeah, minus x minus 2y. Thank you. Okay. So once again, the way you can imagine what's happening here is we're fixing an x value. So once we fix an x value, we'll fix an x value here. Once we fix an x value, we figure out what the y does. So the y is going from here to here. And then once we fix an x and y, we see what the z is going between here and here. Right? And you calculate that area, and then as your x goes from 0 to 6, you're sweeping out and looking at this tetrahedron as being the aggregate, adding up all these very, very thin triangles. Okay. But do you see how this combines what we did last week with just one extra step? The extra step being the sweeping, the up and down, the sweeping of the height. So instead of just integrating the height function, right? Now, if you go back to like examples we did last week, if you did this innermost integral first, you'd integrate the 1 dz and get z, and you would just be integrating the height. Right, so if you think of this integral of the base of the bottom here, the top 1 dz and then dA, however that's set up. When you integrate 1 dz, you just get z from bottom to top. So you're back to the same volume formula we had before. And if this kind of argument looks familiar, it should, because when we used double integrals last week to find the area between curves, this is exactly the same kind of thing that happened, going from a double integral back to a single integral, or vice versa. Okay? So anytime we generalize something in math, it's good to take a step back and show that it matches with what we were doing before. All right, you go through the machinations, you'll get 6 cubic units. Once again, I recommend you work through a couple of these just to make sure you know how the mechanics work. Let's take a look at the order dx, dy, dz. Then we'll set it up this way. So once again, you can think of this triple integral here. Integrating 1 dx, dy, dz. Once again, in rectangular coordinates. These last two, think of them as sweeping out the base, and then this is sweeping out the height. So for this one, they want the base in the YZ plane. So this is the dx, dy, dz. So we're looking in the YZ plane. And so once again, we know what the intercepts are, and we can get the equation of the line there pretty easy. So now we're looking here in this plane. So we got intercepts at 2 and 3. What's the equation of this line here? That'd be the YZ trace. What's that equation? Yep, you'd set the x equal to 0. 2y plus 3z is 6. So we got a y-intercept at 3, a z-intercept at 2. Here's the region, so here'd be the base. So for my volume, I'm going to get going here. 1 dx, dy, dz. So once again, the dz, that's the outermost integral. So we're going to be looking at constant bounds for the dz. So we're going to take this, project it back to the z-axis. We're going between z equals 0 and z equals 2. And now for a fixed z, we got to figure out what the y is running between. So we're going to start here on the z-axis. That's y equals what? Zero. And then for a fixed z, I got to figure out what the y runs between, which means I have to take this equation and solve it for y. So what would you get there? Yep, you do 6 minus 3z all divided by 2. So there we go. And now, this innermost integral, once again, think of this as your height. This is what's going to give you the height. And so since we're with x, we want to go from the back surface to the front surface. Yeah, so if I look at, going back here, the back surface, once again, since we're looking at the first octant, The back surface would be here, which is the YZ plane. So the back would be the YZ plane, aka x equals 0. And then the front would be the plane x plus 2y plus 3z is 6, but I need to know what the x is in terms of y and z. So fixed y and z, how would I calculate the x? So we solve for x. And there it is. And once again, you should get the same answer, 6 cubic units that we got before. But let's see if we could just take a minute and visualize this. When you have a dx, dy, dz, what's going on? Before we do that, though, any questions on how we found any of these bounds? I really think the best way to attack this is one dimension at a time. That's kind of how we've been doing all of this in Calc 3. And then you've got tools to help you visualize it. And then you've got algebra as well. But there you go. So what would this look like visually here? Whoops. Almost flipped the coordinate system for you. So we're chopping up the z from 0 to 2. So here we go. I'm chopping up the z-axis from 0 to 2. And then for a fixed z, the y is going from 0 to 6 minus 3z over 2. So here's the y equals 0, and it's going over here. So we're filling it out this way. And then for a fixed x and for a fixed y and z, the x is running from back here out to that plane. So the it's going to go out to here. Whoops. So I've got this triangle here, and then as we integrate the z, you've got this triangular slice sort of sticking out this way. As we integrate the z, that's going to move up and down, and then that's going to fill out. So for example, when z equals 0, that's what the triangle piece looks like. And then as we move up, it gets smaller until it gets up to the top there. But that fills out that solid. Okay. And I'll leave this one to you. Let's make this your first homework assignment tonight, to look at that one and make sure you can get it. It's variations on the theme. Here the base is going to be in the xz plane. You're integrating the y. So you've got your base here. And then your height. If your base is x and z, then your height's going to be what letter? Y. And so we want y, increasing y, you want to go from the left surface to the right surface. And so see if you can come up with that. Okay. So here's an integral with a given order dx, dy, dz. And they want us to rewrite it with the order dy, dz, dx. Okay, so we have to try to visualize what's happening here. So let's try to piece all this together. And once again, if we need to, we've got a couple different three-dimensional plotters to help us with this. But once again, we can start off here at the outermost integral. 0 to 4, that's integrating along the z-axis. So it's going to chop z up from a constant 0 to a constant 4. So there we are on the z-axis there. So we're chopping that up. And then we're moving in to the y. So if you look at what's happening here, for a fixed z, the y runs between 0 and 1. So y equals 0, that's the z-axis, and it goes over to y equals 1. Which is right there. So this base is actually just a rectangle here. Does everyone see that? And then what's the x run between? So x now, this would be the so-called height. Remember, we go from, so when you integrate the x like this, we're going from back to front. The back would be 2 minus the square root of 4 minus z. This would be the back. And then the front would be 2 plus the square root of 4 minus z. So, once again, it's you might remember what these curves look like. If not, we could always fire up Desmos or GeoGebra. Do you recognize what these will look like? Not quite, well, yeah, not quite paraboloid because there's no y's in there. Yeah, they're parabolic cylinders because there's no y. But let's fire this up here. Let's do x equals. Let's see if this will be a nice test. I've never tested Desmos with this. I know GeoGebra is not gonna. GeoGebra would not like this. Let me get the right equations. 2 minus. Oh, look at that. There you go. Here's a point for Desmos. Unless GeoGebra is updated. There we go. Boom. Okay. So there's the two halves. There's the front and back. Okay. And the part we're integrating over is just this rectangle here. All right. So we're taking. So you can see there the 0 to 4. I'll do it on here. Okay. So here's the 0 to 4. So this is, if you look at the projection here into the YZ plane, we're taking a portion of this. Oh, that's a bad. Color to use here. But here would be like here would be your rectangular strip. You follow? So basically, we're taking a strip of this parabolic cylinder. That's exactly right. Okay. So it's like we're taking a strip of that. Okay? All right. Now, what order do they want it in? They want it in dy, dz, dx. Okay, so this will be interesting. So we've got z between the constant bounds 0 and 4. We've got then y goes between 0 and 1. And then we've got x between 2 minus root 4 minus z and 2 plus root 4 minus z. Now if we want to set this up with the other order, first things first, the integrand, remember, does not change. So if you're changing the order of the integration, the integrand is going to stay xy. That doesn't change. But what does change is we have to now express the solid in terms of this order, which means these last two, once again, we're looking at the base. So the base here would be in the xz plane. So let's sketch what this thing's going to look like in the xz plane. So we can see from from Desmos here that if I look down the y-axis, okay, there's the positive y-axis. Well, actually, we want to go down the negative y-axis. Wait, is that the positive or I can't tell? So we're going to get a parabola. And we want to be chopping up the x-axis, and then we want z as a function of x. So here's what we got to do, is we have to take these expressions, which have x as a function of z, and we got to change them into z as a function of x. All right, so let's look at this one. So what would be a way to solve for z? What would be your first step there? Yeah, so we could subtract 2 from both sides. And then we could do what to both sides? Square. Now notice that negative is going to get squared away, so we'll just keep that as a quantity x minus 2 squared. That would be 4 minus z. And now we could add the z over, subtract the quantity over, but you'll get down to this. And as you could see from the illustration, these are just two halves of the same parabola. Notice that if I had a plus there, the only difference would be there'd be a plus here, but when you square both sides, it doesn't matter if it's plus or minus, we would still get to this point. So that would be our expression. Any questions on solving z there as a function of x? So that's a parabola. It's got a vertex at 2, 4. So we've got now z is 4 minus the quantity x minus 2 squared. There it is. Right. You can check now. We also need the intercepts here, because you notice z goes from 0 to 4. So the 4, that's going to be the top of the parabola. That's the vertex, and then it started here at 0, so we need these values. Can you see what those are just by looking at them? So that would, yeah, be 0 and 4. Once you get one, you know the other from symmetry. Yeah. You plug 0 in. There it is. Boom. So now I know my x. We're chopping up the x from constant 0 to constant 4. And then for a fixed x, what's the z run between? It starts down here, which is z equals 0. It goes up to here, which is our quadratic. And now I need to know what the y runs between. Notice the y is completely independent of the x and the z. Once again, this is a parabolic cylinder. So if I'm trying to figure out the y values that go between, we would go from left to right. So we're just sweeping out the constant y's. And the y's, notice the bounds on the y there had nothing to do with x and z. Oops. So the y's would just remain what? What would the y be? So the y would stay 0 to 1. Yep, they're just the constant bound. So basically, instead of looking at, we're finding the volume of this slice of the parabolic cylinder by taking the area of the base and then multiplying it out. So if this kind of thing sounds familiar, it should. We did one of these like that last week. Okay. So if you remember back from Calc 1 or AP Calc, if you had a continuous function defined over an interval AB, the average value of f over the interval AB was 1 over b minus a integral from a to b f of x dx. And if we think of call the interval I, then this was 1 over the length of I times the integral over I f of x dx. And then last week we generalized that to a function of two variables. So if you had a function of two variables defined over a region, the average value was 1 over the area of R times the double integral over R f of xy dA. Right? So we got this accumulation of the function times the area differential. We divide out that area and we get our average. So you can think of this as adding up. You could think of the dAs if you wanted to as like infinitesimal weights. You add those up and then divide the total weights out. You get your average value. So we can pop over to 3 dimensions. And going from 2 to 3, we tack on the z, so we tack on the extra integral. So we'll have a triple integral over some volume q, or some solid q, and we'll divide by the volume of q. So last week we looked at a temperature distribution of a plate, a two-dimensional object. We could look at the temperature in 3 space. So suppose the temperature at a point in space is given by T of xyz is just the product xyz. Find the average temperature of the block described by Q. Q is the block here, so if we look, we've got all constant bounds here, which is nice. Should be able to find the volume pretty quickly this way. X is going to go from 0 to 1. Oh, okay, great. That's good to know. Thanks, Zach. Welcome in, Saran. So there's 0 to 1 for x. The y is going to go from 0 to 2. So that's that gives you the base here. And then the z goes from 0 to 3. Okay. And so we kind of put that together and we've got our little block here. So this is Q. And so the volume of Q we can get by just taking length times width times height. So it would be 1 unit by 2 units by 3 units. So that'd be a total of 6 cubic units there. Right. And so if I want the average value of the block, so in this case the average value of the temperature, that would be 1 over the 6 times a triple integral over Q of T dV. And so in rectangular coordinates with dV, remember, we have 3 choices for the first differential, 2 choices for the second, 1 for the third. So we have 6 actual possible integration orders. Given that the bounds on all these things are constants and we're integrating over a cube, it's really not going to be much difference what order you get. So does anyone have a particular order they want to do? Everything's even the integrand is symmetric in terms of x and y. So you just pick an order. We could go alphabetical. Let's say we wanted to do that. So t bar would be 1/6 integral of t, which is x, y, z. And if I'm going dx, dy, dz, then let's see what the z is running between. Z is running between 0 and 3. Y is running between 0 and 2. And x is running between 0 and 1. So these are all temperature values being multiplied by volume, and I'm dividing by volume. So in the end, I will get temperature back. Now let's see if what we can do here. Can we split this integral up into factors? So my first integral here is with respect to x. That means I could factor out the y and the z. The second integral is integrating with respect to y, which means I could factor out the z. So if I wanted to, I could rewrite this as 1/6 integral 0 to 3 z dz, integral 0 to 2 y dy, integral 0 to 1 x dx. Everyone see how we can split the integral this way? So this would be 1/6 times z squared over 2 from 0 to 3. That'd give you 9/2. Y squared over 2 from 0 to 2 gives you 4/2. 0 to 1. X squared over 2, 1/2. And then you can go through the machinations here. We get 3/4. And whatever the units of temperature we're using here, degrees Celsius or whatever, that would be your temperature, your average temperature. But once again, hopefully you see going from 1 dimension to 2 dimension to 3 dimensions, you're just basically tacking on that z. It's the same exact concept. You're just 1 dimension up from what we were last week. All right. And then here's your homework here. Once again, I kind of put down every other odd, because that typically gives you about 20 questions or so. If you want, you go back, do every odd. If you need more practice, let me know. I can get you the even solutions. I think I've got access to those still.